Hello, and welcome to the third part of query processing discussions. In the first part of our query processing discussions, we learned about parsing SQL queries, converting parse tree to array tree, and relational algebraic rules that could be used for improving logical query plans. We also briefly touched on size estimations and how they affect cost. In the second part, we discussed query evaluation and examine different algorithms for executing each of the operations and the cost of executing query plans using them. We also discussed models for evaluating expressions that include more than one operation. In this section, we are going to discuss query optimizer. Using and expanding what we have learned in the first two modules, we are going to discuss how a relational database management system optimizes the queries. First, in an overview, we will see how relational algebraic equivalences, size estimations, operation costs, and data statistics can be used in this process. Then, we will focus on the different approaches taken for choosing the evaluation plan at the optimizer. And finally, we will wrap up our discussions of query optimization with a few interesting topics such as multi-query optimization, optimization of updates, and the Halloween problem. At the optimizer, we can apply different models of plan optimization. We can use rule-based optimization, where we replace some expressions with others, similar to what we observed by far with our array laws. The equivalences and array laws are defined laws and are applicable on logical query plans. However, query plan elements can also be replaced based on heuristic rules on different elements, such as access paths. The optimizer can optimize a query plan based on the access paths available and the ranks specified for the available access paths. For example, if a relevant index is available for a query, a rule-based optimizer prioritizes query plans that use the access paths, including the index. As an example, you can check the rules-based optimizer in Oracle. As you may find out in the example link, optimizing only based on rules is not extensively popular and might be supported for backwards compatibility reasons. However, heuristic rules for reducing cost, as we may see later, are used together with cost-based optimization model. More often than not, instead of a complete rule-based model, the optimizers use a cost-based model. They estimate what is the cost of executing a query plan and optimize the plan with the goal of reducing that cost. This involves knowledge or assumptions about size of intermediate relations, algorithms used for operations, and the I/O operations involved in working with the storage. In our discussions, our main focus is cost-based optimizer. It is worth to note that the size and cost estimates are approximations. Therefore, even applying the cost-based model at the optimizer, we might end up with a query that performs suboptimal. Adaptive solutions try to solve this problem. Adaptive plans can be updated during execution based on feedback. For example, a choice of the join algorithm among nested loop join or hash join can be made during execution and based on the size of the input. An adaptive system can also abort a query plan that seems to be performing very badly and not according to the estimated performance. It could then replace it with a new query plan and restart execution and provide the feedback on the less performant query plan so that we can avoid using it again. However, the system should implement this in an effective way to avoid too many abort and restarts.